Hi everyone, my name is Lydia and this is what I wish they had taught me about econometrics and introduction. In the previous video, we showed the intuition behind the law of iterated expectations, and we mentioned that the law of iterated expectations is to the CEF what Jarvis is to Iron Man or what Alfred is to Batman. So in this video, we're going to see the proof of the law of iterated expectations for the discrete case, and there's going to be a separate video for the continuous case. So ultimately, we are going to prove that the expectation of y is equal to the expectation of the conditional expectation. For the algebraic proof, we're going to have a few assumptions first. We're going to assume that we have a discrete random variable x, and this variable x might take like different values like x1, x2, x3, and so on until some xi. Each value xi has a probability pi, and for each group xi, we're going to have this average mu in here equal to the expectation of the conditional y for x being a specific value xi. So basically what I am defining with this neta in here is the average for that particular group. Okay. To do the proof, we're going to start with the definition for the unconditional expectation of the y. And for any one of you who's taken a stats course before, you'll know that this is the sum across all the y's of y, whatever the value of y is, times the probability that y is observed at exactly that value. Now, next we're going to add or one more space, so to speak, one more dimension, because the value of y, we're trying to see it conditional on the value of x. So each outcome y, think of it, can be paired with the value of x. So if we were to write that, what we're saying is that the probability of y being exactly like this small y particular value is going to be equal to the sum across all axes of the probability that we're going to see y exactly equal to a small y, while x is equal to this like particular value of x. Now, if we substitute this into the first line, because remember in the actual definition in here we have this element, then we're going to find that the expectation of y is equal to the sum across the y's, y, and then the sum, p y equals to y, x equals to x. Okay? If we swap the order of the summation, meaning that we're just adding over all the x's and all the y's, then this would be rewritten as the sum of across all x's, across all y's, and then we're going to have y, probability of y equals to y, x equals to x. Okay? Now, if we apply the definition for the conditional probability, which would look a little bit like this. So the probability that y is equal to y, x equal to x is equal to the probability of y being equal to y conditional on x being equal to x times the probability of x being equal to x. Then we're going to rewrite this expression as the sum over x, sum over y, of y times the probability of y being equal to y, conditional x being equal to x, times the probability of x equals to x. Now, the inner sum that you see in here, it's exactly, so this inner sum, it's exactly the conditional expectation of y given that x is a particular value x. So then we can rewrite this as the sum over x of the expectation of y on x equals to x, then times the probability x equals to x. Okay? And ultimately, we started from expectation of y in here. So what that means is that we've managed to show that the expectation of y is exactly the expectation of y conditional on x. Okay. This might still sound a little bit abstract, and for those who don't really like math or statistics, this might really look like a nightmare. So to give you more of that intuition, let's jump into an actual concrete example. Here I've set up a table with some numbers. For ease of computations, I've just taken 10 observations. You can see here we've got 10 people. We've got whether they are low or high. Think of it in the context of like whether you have low or high education, y some outcome variable in here. If we were to find the unconditional mean, so the expectation of y for all of those would be literally the average. So we would have to find basically the sum of all the y's in here divided by the number of observations that I have. You don't have to do all the computations in here. The sum of y for this particular case is 140, and divided by 10, the average in this case is going to be just 14. Okay. Next, the computation of the conditional means. As you can see, for the x variable, I've given two possible outcomes, being either low or high, which means these are the two groups that I'm asking you to find the separate means of. So if we find the expected value of y conditional that x is actually large, this is just going to be the sum of all of the low values over the number, which is just 6, so 60 over 6, that average is going to be 10. Then for the high one, so as you can see, it's just the 4 last observations. The expectation here is going to be 80, the sum of all of these numbers in here, divided by 4, which is equal to simply 20. Now, keep in mind, we have low or high. The probability that x is equal to L, we had only 6 out of the 10, so it's just going to be 0.6, which means that the probability that we have high is only 0.4. Okay? Now, let's apply the formula so that we can really convince ourselves that ultimately we're still going to find 14. So according to the formula, the expectation of the conditional expectation is going to be the number that we found here, 10, okay, times the probability, because remember, we are weighting them, then plus we found that the average for when they are high is 20, and we also need to weigh that by 0.4 in this case. And ultimately, this is just going to give us 6 plus 8, which is equal to 14. And no surprise, it's exactly what we found with the unconditional expectation. Okay, so same result. Why? Because this is like due to that law of iterated expectation. We've basically shown that the overall mean equals the weighted average of group means. Okay. Hope this was helpful. And keep in mind, this was the discrete case. In the next video, we're going to show the proof for the continuous case as well, which is going to require the use of integrals instead of sums. So the same logic will apply. So I'll see you in the next video.